Okay, so what we're looking at here is the TS Analyzer 6200A, and basically this is the analyzer after it's already been removed from the box. There's no real trick to removing from the box, just take out the foam and remove the analyzer. Before doing anything on the analyzer, you got to remove shipping screws, and you also want to take out the plugs that we normally have in the back of the analyzer. So the first thing we're going to show you is how to remove the shipping screws. There are typically 3 to 5 shipping screws in the analyzers. I'll show you where they are. So the first thing you want to do, there's 8 screws holding the cover onto the analyzer. Plus a flathead screw. Get this off, take a couple seconds. And the flathead screw in the back. So in the analyzer, there's 3 shipping screws that hold the main sensor unit to the chassis of the analyzer. These are the screws will be painted red. There'll be 2, one here, and there'll be another one right here. And these are just Phillips head screws. You just want to remove them before working on the analyzer. And anytime you ship the analyzer, make sure you put them back in. There's also going to be one that holds the pump. And the one that holds the pump is located in one of these holes right here. And it'll be red as well. So you can always tell the shipping screws because they're red. On the back of the analyzer, you're going to have all these blue little plugs in it. Okay? Typically there'd be nuts and ferrules on here, but this one doesn't have them right now, but they will have all these blue plugs. Before you start hooking everything up to the analyzer, you're going to have to remove them all. Make sure you remove the one in the scrubber as well. Now, the next part of this system is the converter, the thermal oxidizer, which is this guy right here. There's no prep work, no shipping screws inside here that need to be taken out. The only thing that you want to know is that, once again, there's going to be caps on the back of here that you're going to need to remove before you do any work on it. And the very last part of the system is the dilution calibrator, which is this guy right here.
Now, Eric, not every installation will have the dilution calibrator, but many of them do.
Okay. And so once again, just take off the blue caps. We put these always in every analyzer just to keep stuff from falling inside the analyzer, dust and whatnot. So here's everything. Typically when they're in a rack, you're going to want to put calibrator, analyzer, converter. Okay? This is always the best way to do it. It requires the least amount of tubing, and least amount of tubing, less amount of conditioning that needs to be taking place, stuff like that.
So the calibrator would be at the highest vertical point at the top, analyzer, and then converter at the bottom.
Correct. It does not matter. If you want to do it a different way, you can, but that's the way that I would recommend, just because less tubing means less time for conditioning, less things that can go wrong.
And Eric, typically, how many watts does the whole system dissipate when it's up and running?
Don't know that one off the top of my head. I have to look that one up for you.
But it is important that if we do install it in a rack, that there's sufficient ventilation just to cool the
Yes,
analyzers.
absolutely. They are going to generate heat. The converter runs at 1,000 degrees C. So you can see that it's cooking, it's hot.
Right.
And so you're going to want to have ventilation in your rack. Don't have it be enclosed, otherwise the entire rack's going to get very warm. And you're also going to want to have, as far as power goes, you're going to want to put everything on a UPS if you can. Something that's going to supply nice, constant, stable power. That's the next thing we're going to talk about. If you look on the back of all the analyzers, on all these units, they all have serial number tags. These serial number tags indicate what power these are. For instance, we look right here, power 115/60 hertz. So you're going to want to make sure in the next step when we're going to power these things up that you hook up the correct power plugs to them. You don't want to plug 230 into a 115 analyzer, otherwise it will blow up. So that's the next thing we're going to do, is just hook up power to every one of these analyzers. So right now the analyzers are warming up. I say analyzers, but it's really one only analyzer. They're basically just a bunch of units. We always recommend that you give it approximately 1 hour of being powered on for everything to warm up and come up to temperature. So while it's warming up, we're going to go ahead and connect all the pneumatic connections to it. Okay? You can see there's a lot of fittings, a lot of ports on these back of these analyzers, and they all have to get plumbed up correctly. So what we're doing is first we're going to hook up the actual analyzer over to the converter. One of the things to remember when hooking all this stuff up, always use 1/4 inch Teflon. Don't use any other type of tubing, don't use stainless steel, don't use brass, don't use plastic. Teflon, Teflon, Teflon.
Out of curiosity, Eric, why not stainless steel?
What happens with stainless steel is you will get very, very slow response times. SO2, H2S, all sulfur compounds love to stick to everything, and they love stainless steel. So what happens is it takes a long time to condition and a long time to switch between gases if you're ever switching between gases. Really slow response times.
Is the interconnection tubing supplied when people buy the whole system?
No,
the
not.
customer supplies the interconnection
Correct,
tubing.
yes.
Okay.
So basically all you're going to need is just 1/4 inch Teflon tubing, okay? PTFE. All these fittings that are already on this tubing, these fittings will be on these fittings when you get them, okay? All you need is the tubing. Whenever you make a connection and you take your tubing and put it into a fitting, the first time you tighten that fitting, make it hand tight and then go up 1 1/4 turns, okay? That will bind the ferrule onto the actual nut, onto the tubing, and it'll keep it in place. So first thing we're going to do is hook up the analyzer to the converter. You can see on the converter it says from analyzer to analyzer, and on the analyzer it says to converter and from converter. So what we're going to do is follow that layout. In the first part, from converter, so this one's coming from the converter, and this one's going to the analyzer. This one you just make finger tight, this one you're just going to tighten with a wrench. 9/16. Now hopefully my tubing's just long enough. So the other one from the analyzer goes to the converter over on this side. So now the analyzer is hooked up to the converter, okay? So what happens is the flow rate gets sucked in through the sample inlet, it goes through the analyzer, come back out into the converter, converts all the other sulfur compounds, H2S, COS, gases like this nature, and converts them all into SO2, because that's all this thing measures is SO2. That's it. So now what we're going to do is we're going to hook up the calibrator to the analyzer. So over here it says cal gas out. So we're going to take this cal gas out. And you're going to put it through a T. One half of this T is going to be a vent. You're going to vent it to atmosphere. Because the calibrator is going to put out an excess amount of gas. This analyzer is only going to pull about 500 cc's or so. You're going to want to have at least a liter coming out of your calibrator. And we'll talk about how to set that up in a little bit. But first you want to go through a T. This half of the T is going to be venting to atmosphere. This other half of the T is going to go, we're going to put it to the span gas in. There's multiple ways to set this analyzer up and to do calibrations on it, but we're going to use the span gas in as our calibration point. The sample in is the actual sample. This is what you would hook up to your system. This is what's actually going to read your system and see how much gas is coming out of whatever you're monitoring. So that's the entire pneumatic setup. There's a little bit more on the calibrator, but I'm going to have to turn it around to do it. You see here we have a zero air in. Typically this is where you're going to run, if you're running in CO2, this is where you're going to run your pure CO2. All these ports are going to be under 30 psi. So the zero air in port is where you're going to run your pure CO2, if that's going to be your diluent. And here's where you're going to put your cal gas, where it says cylinder 1. Cal gas, we're going to talk a little bit about that now. We always recommend that you calibrate on SO2 and check on H2S. Now you can calibrate on H2S, but the thing is that over time, what's going to happen, we're talking years down the road, the converter is going to get dirty. Okay? We have particulate filtering, but some dirt's going to make it through and it's going to dirty up the converter. What happens over time is the conversion efficiency in the converter is going to go down. The only way you're going to know that the conversion efficiency is going down is if you're calibrating on SO2 and checking on H2S. So that's why we always recommend to calibrate with a bottle of SO2 and then check with H2S. Because the problem is this calibrator converts most TRS gases in the upwards of 95%. The problem happens is when you start to lose conversion efficiency, the conversion efficiency for each gas is not the same. So let's say we're calibrating on H2S and my converter is only converting at 80% efficiency. COS, which is a harder gas to convert, might be at 40%. And that becomes where the imbalance becomes, when you start losing that conversion efficiency. So calibrate on SO2, check with H2S. So now we're going to turn this around so I can hook up my other gases. So now you can see the front of them. You can see converter, 1000 degrees C. This is always going to operate right around 1000. So over here I have 2 bottles of gas that I hope will reach. Let's move this over a little bit more. What I have here is a bottle of SO2 balanced nitrogen. This is what you want to use to calibrate your analyzer. So I'm going to hook this up using stainless steel line. Whenever you hook up a bottle of gas, be it H2S, be it SO2, always use 1/8 inch stainless steel. Nothing else. And I'm hooking that to the cylinder 1 in port on the back of the calibrator.
Eric, what concentration is the gas in the cylinder?
The concentration in this cylinder is, I think, 25 ppm. This one's 25 ppm. Basically, a standard ratio in this calibrator, it can be used to do many different dilution points. I always recommend around 100 to 1. That seems to be right around where it likes to operate. So we assume that it's about 100 to 1. So when picking your calibration bottle, remember that the calibrator is 100 to 1 dilution. So in this case, I'm running 25 ppm. 25 ppm divided by 100 gives me 250 ppb or 0.25 ppm. So we're going to be operating and calibrating our analyzer at around 250 ppm. So if you're operating on a lower value, let's say you're running on a range of 100 ppb and you wanted a calibration gas of around 90 ppb, then you would choose either up your dilution ratio, or most likely you just want to buy a bottle with less gas in, like 10 ppm, because then you'd get around 90 or so. You get around that 100 ppb range. So first you want to hook this up, make sure that all these fittings are tight. This is 30 psi of gas here, so. Then over here we have our bottle of CO2. We're using a bottle of CO2, as I understand it. A lot of people in the industry just use their own gas, their own CO2. We're just using pure CO2 as supplied by a vendor. And this gets plumbed up to the zero air in port on the back of the dilution calibrator. Now on your regulator, you want to set them both for 30 psi. If you had leak check solution right now, always leak check your fittings. I don't have any here right now. Just bubble solution, bubbles with soap and water. Check your fittings, just make sure they're all tight, no leaks there. You don't want to lose your gas bottle due to a small little leak. So now everything's plumbed up. The next thing we're going to do is we're going to actually look at the analyzer. Especially during startup, you just want to look through and make sure all the values look okay. Make sure nothing looks abnormally weird or anything like that. So the first thing you'll see here is system reset. Anytime the power is reset in the analyzer, you're going to have that warning up on the front panel. This is so you know in case, let's say you have a spike at night in your readings and you want to know why. You come in the morning and you see system reset. There's a power failure. Something happened with the power.
Does the unit, when that happens, will it go back into normal? I mean, is it updating the concentration?
Yes, when it powers back on, it'll go back to operating normally. Everything will be just fine. The only different thing will be there will be a system reset warning.
Good.
So we just hit the CLR button. It stands for clear. Clears out the warning. So now what we're going to do is we're going to look at the different test values. These two buttons are labeled TST, which stand for test. As you see when you hit them, it'll scroll through a bunch of different values. What we're doing right now is we're just going to look through each value and make sure that they look okay. This is very important for the startup because this is ensuring that everything looks okay and nothing broke during shipping. Nothing went horribly wrong. So the first thing that it starts off on is range. This is set by you. Standard is 500. TS stability. This stands for how stable the gas is. Basically, we take a reading of around 240 readings and we take the standard deviation of those 240 readings. That is what you see on the front panel. When you're flowing a calibration gas, if you're flowing 0 or if you're flowing your span gas, this should drop to less than 1.0. It's saying you have a very stable analyzer. Next one is pressure. This is going to typically operate around 5 inches less than atmosphere. So if you're in San Diego like we are and the pressure is 29.7, it's going to be approximately 5 inches less. As you see, 24.9. It's approximately 5 inches less. If you're 5,000 feet in the air, expect it to be a lot less because the pressure is less up there. Sample flow. Sample flow, there's really two ways of measuring it. There's one under air and one under CO2. We monitor mass flow. CO2 and air have vastly different densities. Okay? So what happens is when you go to CO2, you end up having a higher mass flow than on normal ambient air. So you'll see right now on ambient air the sample flow will be around 450 or so. It'll be between 450 and 500. This is standard for just reading air. When we flow CO2, when we start putting CO2 in here, you'll see that value increase. With CO2, it should be around 600. PMT, this is the PMT voltage. On 0, as it is right now, it should be less than 100. We'll talk about span for the PMT in a little bit. UV lamp. The factory set for the UV lamp is around 3,500 millivolts. Over time, this value will drop down. It absolutely 100% will drop down. As you can see right now, it's reading 3,100 millivolts, which is perfectly fine. The UV lamp will last all the way down until it gets 600 millivolts, at which at 600, you will no longer have a reading and the lamp has to be replaced. Once it hits 1,000 millivolts is the time where you want to think about replacing it. You want to actually get a lamp or to do an adjustment, which is on a different video, and you can review that one. Lamp ratio, whenever we do a lamp adjustment, you're going to want to calibrate the lamp. This procedure's in the manual, and I would assume it's on the other video. But you can see it's drifted 16% since the last time it was calibrated. Whenever you calibrate it, it resets this number to 100. Stray light. This is the amount of light that's in that the analyzer sees when there's no gas going into the analyzer. Basically, the way that it works is a molecule of SO2 gets hit with a molecule of UV light. When this happens, this SO2 molecule will fluoresce and put out more light. We measure this specific light. So what this means is this is how much light it sees when there's nothing in there, because everything has dark offsets. So that's what stray light means. This should be less than 100. I think in the manual it says 250, but if you're over 100, something's not right with the analyzer. Dark PMT. The PMT is a photomultiplier tube. What that does is it monitors the amount of light that's fluorescing from that SO2. So that's what we use to detect how much light is coming off those SO2 molecules. The dark PMT is how much the electronic offset of that PMT, how much current it's putting out when there isn't any light in the reaction chamber. This should be less than 50 millivolts. Dark lamp. Just like the PMT, we have another detector that monitors the UV lamp to see how bright that is. Just like before, it's got a dark current. Something when there's no light hitting it, how much current is it putting out? This should be less than 50 millivolts as well. Slope. We'll get into slope when we calibrate, but slope should be around 1.0. As time goes on, the slope will drift down. The reason being is, for the same amount of gas we're putting in the analyzer, the PMT is picking up less light. Whether because windows are getting dirty, or because the UV lamp isn't putting out as much light, but over time, the slope will slowly drift up. And we'll go through and how to set the slope in a little bit. Offset, this is just how much there is when it's reading 0. HVPS. This is how hard we have to drive the PMT to give us a slope of 1.0. And we'll talk about that in a little bit more when we go into the calibration. But just know, HVPS should be less than 800. If it's not, something's wrong. DCPS, direct current power supply. This is a sum voltage of the 15, negative 15, 5 volts, and positive 12 volts. This should always be around 2,500 plus or minus 200 millivolts. If it's not, then there might be something wrong with one of your power supplies going bad. R cell temp, this is the temperature of the reaction cell, should be right around 50 degrees C. Box temp, this is the ambient temp of the box. So like we said before, if you have a rack, and if you want to know if it's getting too hot in the rack, you can look at the box temp. This should be right around ambient temperature. It might be a little bit hotter, but if it's reading upwards of 40 degrees C, that's when you might start to see a problem. Anything below 40 degrees C and you're pretty much happy. PMT temp. We cool that PMT to 7 degrees Celsius because it gives us less of a dark current at that low temperature. So this should be around 7 degrees C. Time, is the time. And so that's all the test features. So the first thing you want to do, power it up, look at all those values, make sure everything looks okay. For instance, pick one at random here. If I came in and I saw my stray light was reading 2000 millivolts or 2000 ppb, something would be wrong. And then I'd have to find out what's going on or give tech support a call and talk to them.
Eric, how long would you recommend that we wait before we start looking at those readings on the front panel?
1 hour. You can see we didn't wait an hour for this, and it'll be perfectly fine, but always give it an hour for everything to warm up. That's always recommended for every one of our analyzers. We look over here. The only thing you need to do with this one is just make sure that it's 1000 degrees C. If it's monitoring 1000 degrees C, you're okay. You'll see there's a little light that says PV and SV. The PV is what it's currently reading. If I hit this PV-SV button, this is the SV, this is the set point. So you want to make sure that that PV is lit, otherwise the set point will always be 1000. So you just click over, make sure the red light comes on PV, and that it reads 1000 degrees C. There is no startup procedure that needs to be done on the calibrator. It's already good to go. So that's everything when you're first powering up that you want to check. So the next thing that we need to do is everything's hooked up. We need to actually get some calibration. We want to calibrate our analyzer. We've got our gas, we've got our analyzer and our calibrator. We need to actually calibrate our analyzer. So what we're going to use to calibrate this is we have to monitor the flow one time coming out of the calibrator. This is designed to put out one flow, one concentration of gas, but to put that concentration out very precise every single time. So what we have to do first is measure the flow coming out of this, both for the dilution and for the cal gas. And so we'll show you how to do that next. What I have here, this is a BIOS. This is a very precise flow meter. This is what you want, something that's a very precise flow meter. This is what you need to monitor the flow. You're going to have two flows. One that's going to be less than 100 cc's, one that's going to be less than 5 liters. So you're going to want something that can measure the flow accurate between 0 and 100 cc's and 0 and 5 liters. So I've got my flow meter. What I need to do now is I need to hook the flow meter up to the cal gas out on my calibrator. So you can't see it, but what I'm doing is on the back of the calibrator, I'm disconnecting that line that says cal gas out. That's going to the span gas 1 in that we put through the T. So I'm disconnecting the cal gas out port and hooking up my flow meter to that port. So now on my BIOS, I've got our 100 cc meter reading right now. So what I'm going to do is you've got a few buttons on here. What the diluent button does is it turns on the diluent. So when I hit this button, you'll see this one shoot up. This is the pressure. This is like a set point. This is kind of a set point for the flow. Basically, we vary the flow by varying the pressure. So hitting this diluent button turns that pressure on and off. The only one we're worried about right now is the cal gas flow. So what we're going to do is we're going to hit cylinder 1. This opens the cylinder 1 that we hooked our stainless steel line coming from our gas bottle to. So I'm turning down the cal gas flow. Typically, you'll want to put it somewhere around the neighborhood of 15 psi on this front panel. You can see right now it's reading about 15 psi. So now what we're going to do is we have our BIOS set up. I'm now going to, right now, our CalGas flow is coming from our bottle, going through our flow regulator with the pressure, which is controlled with pressure, and it's coming out of the CalGas out port on the back of the 702, or the dilution calibrator. So what I'm going to do now is I'm just going to measure that flow with my flow meter. And with the BIOS, this can take a little while to do. What we do is we take 10 readings of this flow, and then we take the average of those readings. This is a very precise measurement that you want, so you do not want to rush this. While this is doing its thing in measuring the flow, I'm going to come back here and look at the actual concentration on my gas bottle. On my gas bottle, I have 25.40 ppm. So I have to know that number for my calculations. So I want to remember that number. What we're going to do is once we measure these flows, we're going to plug them into an equation. And I'll draw this equation up for you real quick. C equals So, I don't know if you can zoom in on that and see that equation there.
Let me try.
Tell me if I need to bring it up closer or not. If that helps out at all.
We got it.
Okay. So this is the equation to calculate what concentration is coming out of the calibrator. Basically, you've got the CalGas flow divided by the sum of the CalGas flow plus the diluent flow, which is the total flow. So this sets up your dilution ratio. Basically, we're diluting this amount of CalGas and it's going into this amount of total flow. You take this dilution ratio, multiply it times the bottle concentration. In this case, our bottle concentration is 25.4. Our bottle concentration is 25.40. So after we find the CalGas flow and the diluent flow, we can plug all these numbers into our equation and come out with the concentration at the back of the analyzer. So it looks like my CalGas is done reading. And on here, I've got a flow rate of 18.93 cc's. So this is equal to my bottle. Would it be better if I drew up on the board?
No, that's fine. I have it.
Okay, excellent. Okay, so I've got my CalGas flow. I know how much CalGas I'm flowing out right now. The next thing I need to do is find out how much diluent flow I'm having. So I need to turn off cylinder 1. This stops the flow coming out of my gas bottle.
How did you do that, Eric? You pushed the top right button?
Yeah, the button that says cylinder 1. If it's lit, that means the gas is flowing. If it's off, it means the gas is not flowing.
Perfect.
We close the valve. So for my flow meter that I'm using, I have to use a different piston.
Are the pistons individual for each type of gas?
They're individual for the amount of flow rate.
The range.
Yeah.
Okay.
This one's around 0 to 100, 0 to 10 liters. This one's around 0 to 100 cc's or so.
Gotcha.
They can measure more than that, but that's pretty much what I like to use. So now what I'm going to do is make sure my cylinder 1 is turned off, first off. I'm going to look over at my diluent. I'm going to turn on my diluent. Once again, I'm going to set this for about 15 psi. So now what I'm going to do is I'm going to run this and see what I get here. Doing the exact same thing I did before, this time only the diluent flow is coming out. And something's wrong with my bottle. Maybe I did not open it. There we go. Yeah, make sure your bottles are on. So we got 15 psi. So now what we're going to do is we're going to measure the flow rate coming out.
Do you guys recommend that the dual stage regulators get purged before connecting?
Yes, yeah, absolutely. I didn't show that part, but yeah. Basically, anytime you hook up a regulator, the way you always want to do it before hooking everything up to the analyzer is just have this vented out to the atmosphere and just basically we call it burping the bottle. What you're doing is you're opening the bottle and letting gas flow through into this portion, close the bottle, then open up the vent to atmosphere. What this is doing is it's filling up all your tubings and all your lines with the bottle concentration, and you don't want to get any ambient air. Because ambient air can actually flow backwards into the bottle. And this becomes a very big problem in some cases. Because what happens is you get a vortex effect. So you've got this gas that's flowing across this way, but occasionally you'll get some gas that vortex and spins backwards and goes down into the bottle. We've seen it happen before. It's a very rare phenomenon, but it can happen. And if it happens, you just lost a bottle of gas. So always do what we call burping the bottle. Fill up the regulator, close the bottle, open the regulator, let that gas vent out, close this again, fill up the regulator, and then let it flow out, and you can hook it up to your analyzer and you're good to go. This is with any bottle of gas that's not going to kill you if it vents to the atmosphere. All this concentrations, 25 ppm of SO2, these are perfectly fine. So now what I have here is I've got a reading. My flow rate is 1277 cc's, or 1.2 liters. I wanted to get about a 10 to 1 dilution ratio. So what I'm going to do is I'm going to increase this a little bit more to get that 10 to 1 dilution ratio. 100 to 1 dilution ratio, sorry. So what I'm going to do is I'm going to increase the pressure up here a little bit. I'll go ahead and put it to 20 psi. And see what I'm reading. Basically, you would do this until you got the desired flow rates that you're looking for. That dilution ratio that we're talking about here. Basically this, 10 to 1, 100 to 1 is what we're looking for. And this divides by this, approximately. Doesn't need to be exact, just approximate. Basically, you're trying to get your desired cal gas. So right now I've got 1700 cc's. That's pretty close. I'm going to increase it just a tiny bit more. And see what I read now. So right now I'm going to be reading around 1840 when this completes. So 1840 and 18.93 is about 100 to 1 difference. And when we do the calculations, we'll find out exactly what the dilution ratio is. So I'm reading 18.36. Or sorry, 1836. 1,836 cc's. So, 1836. So now what I'm doing is I'm punching all these numbers into the equation down here. So I take my cal gas flow, 18.93, and divide it by my cal gas flow, 18.93, plus my diluent flow, 1836. When I get that, I come up with 0.01. Sound right? Make sure I did that right one more time. Yeah. So when I do that, I come up with the number 0.102. Or 0.0102. Make sure I'm doing this right here. Yeah. So I come up with the zero of the number 0.0102. If I want to figure out my exact dilution ratio, I take 1 and divide it by this number. And this is what tells me my dilution ratio. I got 98. So I've got a 98 to 1 dilution ratio right now. And I was aiming for 100. It's pretty good to me. So now what I'm going to do is I'm going to take this number, this 0.0102, multiply it times my bottle concentration, and that'll give me the concentration going to my analyzer. So 0.0102 times 25.4 ppm gives me 0.259. So my concentration, I'll bring it back up in a second. So my concentration is equal to 0.259 ppm, or 250 ppb, 1,000 to 1 ratio between ppb and ppm. So I know what I'm going to flow to my analyzer. So now what I want to do is I actually want to flow that gas to my analyzer. So I'm going to turn on both cylinder 1 gas and the dilution. Now I'm actually diluting my cal gas, and I'm flowing it out the back of my calibrator. So what I'm going to do now is I'm going to disconnect my flow meter that was hooked up to my cal gas and re-hook up to my buttons on the front there.
Okay, so where we left off, we had just used the BIOS flow meter to calculate the flows on the diluent and the calibration gas cylinder. And we've done that. We've come up with a calibration gas value of, I believe,
259.
259 ppb. 259 ppb, and now Eric's going to show us how we proceed with the calibration of the analyzer.
So now, real quick, I'm going to move this over one because I want to take the top off.
Oh, do we need to zero it first, or no?
Basically, I always recommend doing a span first before you do a zero.
You do a span before the zero.
Correct.
Okay.
Because it's going to affect it. It's going to affect the zero a lot if it's way out.
Oh, okay, gotcha.
So right now, we want to make sure diluent and cylinder 1 flows are both lit. If both these lights are lit, we know that both the gases are flowing.
Gotcha.
So now I have that 259 ppb coming out of my calibrator, going to my analyzer. So now what I need to do is I need to hit the Cal S button. Hitting the Cal S stands for Cal Span. Remember, we hooked up our calibrator to the Span Gas 1 import on the back of this analyzer. So I hit this button, a valve now triggers, and now I'm sampling not from the sample port anymore, but from the Span Gas 1 port. And we should see this number start to increase in a few minutes. We always recommend that you give this analyzer enough time to stabilize out. Very, very, very important. If you try and calibrate this analyzer without it being stable, you'll have tons and tons and tons of problems. So you can see the concentration starting to increase. And while that's doing that, I'm going to remove the cover. And I'll be right back as soon as I get a pot tweaker. Concentration is flowing.
Hold it back up. I had put it on pause. Okay.
Okay.
Sorry.
So, the concentration is flowing to the analyzer. We now need to calculate what we call our target PMT value. Okay? So we scroll through here, and I think this was an old one. But we've got two things. We've got a PMT or a norm PMT. This one doesn't have it. It's a version of software that doesn't have it. If you have a norm PMT, the equation is simple. It's 2 times the concentration plus the offset. So our concentration is 259. 259 times 2 is about 5 something, 520. 518. So 518 plus our offset of 55 millivolts gives us 573. This is what we call our target PMT value. This is for the norm PMT. In the case of this analyzer, we do not have a norm PMT. So if you don't have a norm PMT, you have to factor in one more thing, and that's the pressure. So what you want to do is scroll over till you get pressure. And you want to take whatever the current pressure reading is, so 25.6, and divide it by 29.92. That happens to be 1 atmosphere. So 25.6 divided by 29.92, take that number and multiply it times the norm PMT target value. of 573. So we come up around 490. So we're looking for a PMT target value between 490, anywhere around 490. Doesn't need to be dead on, but you want to be close. As you can see with this analyzer, it needs a little bit of adjusting, as our PMT is only reading 284. That's why our concentration is only reading 141 when we're putting the gas in. So what we need to do is we need to adjust. This is what we call a factory calibration. And this will need to be performed on the analyzer at some point in its life. So what I'm doing is I'm taking the cover off of the preamp. It's 2 Phillips head screws. That remove this cover. All this stuff is low voltage, so you're not at any point worried. The only part that you need to worry about being shocked a little is right here on the pump, because that's 120 volts. That's the only spot. So we've got our preamp board here. This is all covered in the manual, but we'll go through and just show you how to adjust it real quick. So our target PMT voltage is around 490. So what I'm going to do is I'm going to look at my PMT value, and I see it's reading 289. You've got 2 hex switches right here and right here, called S1 and S2. These are coarse and fine. S1 is the fine, S2 is the coarse. These adjust the HVPS, which adjusts the PMT. So what we're going to do is we're going to click these up and turn them up, because our PMT value is too low. If our PMT value is too high, then we turn it down. So I just turned it up 1 click. I'm going to look back at my PMT value and see what it reads. 585. It's a little high now. So I adjust the coarse that time. So I'm going to take the fine and back it off a few clicks. I turn it down 3/6. Counterclockwise is to turn it down, clockwise is to turn it up. So I go back here, look at my PMT voltage, 528. It's still a little high. I'm going for 490. So I'll click it down a couple more clicks and see what it reads then. 480, 470. So we're close.
Just went to 489.
So once you get close, if you want to get closer, you're going to use R19. It's called the span pot. This one will get you as close as you can. It's this little potentiometer right there. You can see there's a little tiny screw head on the top.
Yeah.
So we adjust that. And it'll increase the PMT a little bit as well. So right now I'm around 490. You can see now our concentration has got a lot closer to our target value of 259. When we calibrate it, it'll make it a lot closer. So it's still at 0.8. Okay. Once you get close, you're going to see that the slope is still a little bit off. So what we're going to do is we're going to first wait for the analyzer to get stable. And there's 2 ways of making sure it's stable. The way that you want to do it is to look at TS stability. This number will eventually drop to less than 1.0. When that happens, that's when you want to calibrate. If you look at this value, you'll see that eventually it stops changing. So what you want to do is you want to wait till this value gets to less than 1.0 and calibrate your analyzer. Sometimes the slope equation doesn't fit exactly how you think it should, so we need to use the slope to modify our target PMT value again. So our target PMT value is 490. What we're going to do now is we're going to tell it the concentration that we're putting in. So we're putting in 259 ppb. So we hit the CONC button and change this to read our target value of 259. So I'm putting in 259. Now, let's imagine this was stable. Typically you want to wait 15 minutes. If this stability was less than 1.0, we would then calibrate the analyzer. To calibrate it, you hit span, enter. and you'll see that my TS reading now just went straight to equal 259.
What does TS stand for?
Total sulfide.
Ah, I see.
Basically, you've got two types of gases, TS and TRS. Two types of measurements. TS is total sulfur. It's all sulfur compounds. TS is total reduced sulfides. It's all sulfur without SO2. So basically, a lot of times people will have an SO2 monitor and a TRS monitor. So after we do the calibration, we're going to scroll over and look at our slope and see what it reads. You see it's reading kind of low. We want it to be around 1.0. So what we're going to do now is we're going to take our target PMT value of that 490. We're going to divide it by the slope. Go up. Sorry, we're going to multiply it by the slope. Okay? So you take this, multiply it by the slope of 0.798, and this gets us our final target PMT value. I got 391. So just like we did before, we're going to adjust the norm PMT for 391 being the final PMT value. If you have a norm PMT, this is why it's good, all these calculations are done for you. Most new analyzers have the norm PMT value in there. And it does all the calculations for you. All you need to know is 2 times the concentration plus the offset. So I'm going to adjust this down a little bit. Just using S1 and S2, just like I did before. And I was shooting for 390. So right now we're around 390. And once again, we're going to want to let it stabilize out. So I'm going to go back and look at the TS stability. TS STB. And once again, I would wait for this thing to become less than 1.0. This is very important to do correctly the first time because it sets up how the analyzer is going to react until you do it again.
Eric, what is it that is driving the stability of STB? What is something warming up or cooling down? Or?
What this number is the standard deviation. We take about a 6-minute moving block of numbers. So every 6 minutes, so every time we get a number in, one reading comes in, the last one kicks out. We then take the standard deviation of that block of numbers. So we've got, let's say, 200 readings in this block of readings. We take the standard deviations of those readings. So what happens is, I'll throw it up on the board real quick. That way you can see exactly what's going on. So what we have here is a concentration versus time. As we flow gas into the analyzer, it starts off at 0, and you'll see it go up like this. And becomes straight right here. Imagine that line straight. What happens is, as this is increasing, and we have a moving block of numbers, at this point in time, the stability is very high. When this moving block of numbers gets over into this region right here, the standard deviation is very low. So what happens is, as the concentration is increasing, right here, right there it's stable. But the thing is, my stability is still going to be very high because my moving block of numbers is this big. So what we do is we make sure that it's been stable for a while before we do our calibration. That way, in case there's a little burp of gas here or something like that, we won't calibrate it until it's been stable for a certain period of time. So that's why always make sure your stability is less than 1.0 before you do a calibration. Otherwise, you're just going to run into a lot more troubles and it's going to take you a lot longer time fixing those problems. So for right now, we'll imagine we went 15 minutes into the future and my stability is now 1.0. If we keep watching it, you'll see it all of a sudden just take a drastic drop and be very close to 0. Once again, we're just going to calibrate the analyzer, span, enter. Now when we look at our slope again, it should be right around 1.0, 1.021. It's great. The spec for the slope that we recommend is that you keep it within 0.9 and 1.1. So 1 plus or minus 0.1 is where we recommend you keep it. And you can see it right now, perfect, wonderful. So you've just calibrated the analyzer on span gas, now we want to calibrate it on 0. Typically in the analyzer, what you're going to want to do when you calibrate it on 0 is just hit this Cal Z button right here. What this does is it pulls in sample gas. Okay? I don't have CO2 hooked up to my span gas port right now, so I'm just going to run my calibration gas over there as a CO2 source. But typically what we do is when we do our 0, we 0 it on span gas. On sample gas, sorry. We take the sample gas and we run it through an internal scrubber. That scrubber scrubs out any SO2, any H2S, any sulfur compounds, and then we 0 it on that. So I hit Cal Z, and now what it's doing is it's pulling in through the sample, it's pulling in your system gas, running it through the analyzer, and through an internal scrubber. This is right here, don't know if you can see it. Right here.
Right there, gotcha.
Okay. So internal scrubber right there. The gas now flows through the scrubber and back in through everything. So once again, just like before, we're going to give it time. You see there's no concentration button here this time, that's because 0 is 0. So now what we're going to do is we once again look at the stability and wait for it to drop to less than 1.0. When it's dropped to less than 1.0, you're just going to hit 0, enter, and then you're done. Analyzer's been calibrated, everything's been great. The only thing I recommend you do is just flow span gas one more time, make sure that it spans up correctly and everything looks good.
The 0 button is the furthest left.
It's this one right here.
Oh.
Third button.
Okay, you just simply hit enter. Okay.
Yeah, so you hit the Cal Z button to put it into the 0.
Yeah.
And then you have a 0 button right here. It's basically a 2-button press, that way you can't accidentally hit the button.
Gotcha.
So you hit 0, and then you hit enter, and it zeroes it. As you can see right there, I accidentally hit the button. So you would just wait for the stability, less than 1.0, hit the 0 and the enter button. You'll see the TS will go down to 0. It's still dropping right now because I haven't given it enough time. Once again, 15 minutes always, unless you just want to sit here for 15 minutes.
No.
Yeah. So, and that's pretty much everything with the analyzer.
Wonderful.
Any other questions there, Steve, that you might have?
Eric, many of the Teledyne customers looking at using this system for monitoring the purity of CO2, some of them do not have the calibrator. Is the procedure to calibrate and 0 the unit basically identically to what you've described, with the exception of simply not using the calibrator, just hooking up the cylinders in the back of the unit?
Correct. You would just hook up cylinders of, most likely it's hard to get cylinders of gas at the low concentration that you're looking for. So 99% of the time you're going to have some way you're diluting the gas. Whether you're using our calibrator or some other way to dilute it, doesn't matter. You hook it up exactly the same way. Just make sure that whenever you're hooking anything up to the analyzer, it's always at ambient pressure. Very, very important. If I look at the pressure reading on my front panel of 25.5, that value should not change more than 0.1 or 0.2 inches, being if I have a tube connected or disconnected. It should read almost exactly the same.
Very good. And are there any specific precautions that one needs to take when one is connecting the output signals, such as 4 to 20 milliamp or relays or things of that nature?
The only thing when hooking those up you want to make sure is, for instance, the 4 to 20 milliamps, you don't want to put a voltage on these lines. you're just hooking them into your input devices, to your data logger, your strip chart recorder, your PLC, whatever you're using to hook up to the analyzer. Just make sure you're hooking them up right. If you hook them up wrong, you can blow stuff on the VDAP board.
So the analog output, the 4 to 20, requires a passive load. What is the maximum resistance that output can drive? Do you recall?
Do not know off the top of my head. Do not know.
If it's like some of the other equipment, I would say typically 200 ohms or something like that. Does that sound about right?
Typically you run 200, 250 ohms.
Yeah.
Somewhere in there.
Good. Good. And the relays, normally in this, are solid state relays, so it's important that
Correct.
if you are connecting to those relays that you observe the proper loading parameters in the manual.
Which is 25 volts, 50 milliamps.
Eric, briefly, what would be involved, let's say we wanted to, for whatever reason, decommission the units either temporarily or move them to a new location? Is there a specific order that it's best to power things down in and things of that nature?
Basically, you can just power everything down. I mean, just power. You're good to go. Keep in mind that this is still at 1,000 degrees C, so you might want to let it cool down before you do anything with it.
Good point.
If you happen to have a perm tube in your analyzer, you must remove this every time you power it down. Okay? What happens is perm tubes will constantly outgas no matter what. So even if it's sitting around on a shelf somewhere or in the back of a truck or being moved, that perm tube's still putting out gas and it will contaminate the analyzer. And it might take a week of running before it gets uncontaminated, or it might never get uncontaminated. So always remove the perm tube. Once again, you remember the shipping screws were removed previously? Reinstall them. It's very important because what can happen is if the shipping screws aren't been removed, this thing can break loose if it takes a large jarring.
Well, thank you very much, Eric.
You're very welcome.
Excellent work. Appreciate your help.
Okay.